The last topic for this chapter is the integer arithmetic. So in this topic, you are going to learn how to do the addition, the subtraction, the multiplication using Boost algorithm for 2's complement number, and also for division, which is the restoring binary division algorithm for unsigned numbers. This is how you want to do the negation for 2's complement notation. So in this example, you can see that when you want to do the negation for positive 18, you take the 2's complement number, which is 0, 0, 0, 1, 0, 0, 1, 0. After that, you do the bitwise complement or you do the flipping and you add 1. And the results, what you get is 1, 1, 1, 0, 1, 1, 1, 0, which is equivalent to negative 18. And the same thing when you want to convert or do the negation from negative numbers to the positive numbers, you do the same thing again. You take the 2's complement number and then you change to the bitwise complement, or you do the flipping and you add 1. And it becomes 0, 0, 0, 1, 0, 0, 1, 0, all equals to positive 18. This is the special case of the negation. The example is 0 here. So in this case, we need to take 2's complement with 8 bits of 0. And then we change to the bitwise complement or flip the numbers. And after that, we add 1 to the LSB. So the result is 1, 0, 0, 0, 0, 0, 0, 0, 0. But in this case, the meaning of the negation, we want to change from the positive numbers to the negative numbers. But in this case, for the number 0, we only need or we only cater for 8 bits of number. But the results produced here is 9 bits numbers. So we need to ignore the MSB part because this one is considered as an overflow. So meaning that the special case negation for number 0, from the positive to the negative, it cannot be negative because the overflow is not counted. So the results is maintained 0. When we do the negation, it's still the results is still 0. For the addition integer arithmetic, so basically this one is very straightforward. You just do the normal addition for the binary numbers. The thing that you must careful is the negative numbers. Alright, so the negative numbers you must always convert to the 2's complement. Remember that inside topic 2, okay, when you got negative numbers, you must always convert to the 2's complement. For this example, you got negative 7 plus or add to 5, positive 5. So negative 7, basically you need to convert to the 2's complement. And 2's complement for negative 7 is 1001. Okay, and then you do the normal addition with the positive 5, which is 0101. So you got 1110. So here you can see that at the MSB here is 1. So meaning that this is the negative numbers. How you want to know that this is the correct or the correct additions or the correct results that you got? So you need to convert back to the 2's complement. When you convert to the 2's complement, then you will get number 2. And this one negative, the MSB here 1, meaning that this is the negative sign. So this one negative and this one is 2. All right. So that's the simple or the straightforward operation for the addition. And this one basically it want to show the overflow. Another overflow rule is that if two numbers are added and they are both positive or both negative, then overflow occurs if and only if the result has the opposite sign. So basically in our computer, it has the overflow sign to indicate to flag the computer that the overflow happens during the arithmetic operation. The next arithmetic operation is the subtraction. Okay, so here you must know the rule of the subtraction. To subtract one number subtrahend from another minuend, take the 2's complement negation of the subtrahend and add it to the minuend. So basically, if you see the first example here, 2 minus 7, okay, 2 minus 7, 2 is considered as minuend and 7 is the subtrahend. Okay, so we look at this part. Okay, so this one, 2 minus 7, okay, 2 subtract 7. So basically, this 2 is the minuend and negative 7 basically is the subtrahend. And then remember, when you got the negative numbers, you must convert to the 2's complement. So you need to convert negative 7 to the 2's complement and then you do the normal addition. Okay. For example here, for the minuend, this one is positive 2. Okay. So this one too. So in binary numbers, it is 0, 0, 1, 0. Okay. For negative 7, when you convert to the 2's complement, okay, still remember how you want to convert to the 2's complement, right? Okay. So this one's 7 is 0, 1, 1, 1. Okay. For the 1's complement, you got 1, 0, 0, 0. And for the 2's complement, you need to add 1. So you got 1, 0, 0, 1. Okay. So this one basically is the 2's complement for negative for number 0. Okay. So this one you need to do the this one 1, 0, 0, 1. So you do the normal addition. Okay. So this one becomes 1, 1, 0, 1. Okay. So instead of you do the subtraction, okay, you just convert this negative 7 to 2's complement and then you do the normal addition. So that one is the easiest part. Okay. So you got the results here, 1, 0, 1, 1. Okay. So the rest is regarding the overflow for the operation. This is an example of the block diagram of hardware for addition and subtraction. So I'm not going to elaborate more on this block diagram. It's just to let you know that in our computer there are certain hardware. Okay, there are certain hardware that is used for the addition and subtraction. Okay, for example, we use the register. And then we do have the complementer, and we use switch, okay, to switch either to do the addition or subtraction, and we do have the adder component and the overflow component. This one to give signal to the computers whether the operation gives overflow or not. For multiplication arithmetic operation, okay, so this multiplication, it has its own algorithm. You can use the traditional calculation, okay, the traditional calculation for multiplication, but it is more convenient using the algorithm, or it is better for you to know how to use the algorithm, because that one basically is used in our computer. Okay, for algorithm, it has for the unsigned numbers, meaning only for positive numbers, and we also have the multiplication algorithm for 2's complement, whereby it has two types of number, positive and also the negative numbers. So this multiplication process can do for both positive and also negative numbers. And for this course, we are going to focus on the algorithm for the 2's complement, which is the boost algorithm. Alright? This is the hardware. Okay, this is the hardware used, and this is the flow chart for algorithm for the unsigned integer. But I'm not going to elaborate more on this because we are going to focus only for the two's complement, positive and negative numbers. This is for your knowledge only, the unsigned integer. This is the hardware, and this is the hardware diagram, and this is the flow chart how to conduct the multiplication for the unsigned integer only. Okay, for the two's complement multiplication, or we call it as the Bose algorithm. This is the process of doing the Bose algorithm or the multiplication using positive and also negative numbers. Okay. So this one I'm going to record another video one by one how you want to do the Bose algorithm. Okay, I will show you manually on how to use the Bose algorithm. For this video, I'm going to explain how to read the flowchart. Okay. So this is the flowchart for the Bose algorithm. So this is the starting point of doing the Bose algorithm. So A is the accumulator and Q minus 1 is another register. Okay. So A and Q minus 1, you must always initialize the value with 0. And the value, the number of bits, it depends on the architecture of the computer. If the architecture of the computer, it only cater for 4 bits number, so meaning that the accumulator and Q minus 1 register must contain 4 bits of 0. Okay. M register for multiplicand numbers, Q register for the multiplier numbers, and N is the count numbers, right? So go to the this condition, you must what we call compare Q0 with Q minus 1. Okay, Q0 and Q minus 1. So if Q0 and Q minus 1 is 0, 1, so means that you must do the addition process. Alright, and then you need to do the arithmetic shift right for A accumulator, Q register, and Q minus 1. Sorry, this one Q0 and Q minus 1. Okay, and the count, which is N, need to minus 1. Alright, Q minus, so arithmetic shift right for A, Q register and Q minus 1 register. Okay, so you need to do the arithmetic shift right, and after that you need to minus 1 for the count or for the N. Okay, so if the count not yet 0, okay, not yet 0, meaning that you need to repeat the process. You need to do the comparison for Q0 and Q minus 1. If count is 0, then you need to end the process. Alright, for if Q0 and Q minus 1 is 1 and 0, then you need to do the subtraction process. So remember, if you receive the subtraction, this one, the subtrahend, you need to convert to the two's complement. Okay, you do the normal, after that you do the normal addition. After that you do the arithmetic shift right, and then count minus 1. If Q0 and Q minus 1 is 1, 1 or 0, 0, and then you just do the arithmetic shift right. No need to do the other operation, subtraction or addition. Okay, you do directly the arithmetic shift right, and then count minus 1. If count not 0, then repeat the process. If 0, then you end the process. Right, so you can find the video, okay, on the Bose algorithm, which is manually, I show it manually how to do the Bose algorithm. The last arithmetic operation is the division, right? And for this course, we only focus on the unsigned binary numbers for the division, or we call it as the restoring division algorithm. You can use the normal calculation like subtraction, like addition, okay. But this one is very much tedious. You can use the alternative for this one. You can use the algorithm. Okay, since we focus on the unsigned binary numbers, so the algorithm is called as restoring division algorithm. How you want to do the restoring division algorithm? This is the flowchart for the restoring division algorithm. All right. For this part, okay, for this part, you need to find another video, which I manually show on how to do the restoring division algorithm. Okay. For this part, for this video, I only explain on the flowchart. So basically, this one is also similar like the multiplication, the boost algorithm, but the different is the shifting part. For the boost algorithm, the shift is the shift right. For the restoring division algorithm, the shifting should do at the left part. All right. Okay, we start with the flowchart. Okay, we start the flowchart. The accumulator should start with 0. M is the divisor. M register should contains the divisor, divisor bits number, and Q is the dividend. Q register contains the dividend bits number, and N is the count. All right, and then do the shift left for the accumulator and Q register, and then do the subtraction. Again, for the subtraction, subtrahend, you need to convert to the 2's complement. Okay, and then you do the normal addition. After that, you do the comparison for A. Okay, so A means that the MSB of A register, the bits number or the binary numbers in A register, you need to look at the MSB. All right. If the MSB is 0, so means that it is negative numbers. If MSB is 0, so meaning that it is a positive numbers. If MSB A is 1, so means that it is a negative number. If it is a positive numbers, so it will go to the no direction. Okay, it will go to the no direction. So Q0, you should restore with 1. After that, you count minus 1. Okay, if MSB inside A register is 1, so meaning that it is negative numbers. If negative numbers means that it is less than 0. If less than 0 means that you need to go to the yes direction. When you go to the yes direction, process that you need to do is Q0, you need to restore with 0, and then you do the addition. After that, you count minus 1. Okay. If count is not 0 yet, then you need to repeat the process. If count is 0, then you need to end the process. Okay. So you need to find the video on the restoring division algorithm on how to do this division part.